Hello, I'm Steve Halliday, and I'm a member of the Developer Relations team at Imply. My focus on the team is to create training curricula that helps Apache Druid users be more successful and effective. You can check out some of my work at learn.imply.io, where our team provides courses like Druid Basics, Apache Druid Data Modeling, Druid Multi-Stage Queries, and the most recent addition, Druid Logs. Apache Druid performance can be sensitive to the type of data it stores. Of course, the data we store in Druid will be time-centric, which is to say that the timestamps are the primary partitioning mechanism. But other dimensions of the data affect Druid's behavior as well. Sometimes, we would like to know how well Druid will work for a specific type of data, and sometimes that data isn't available for testing. The data may not be available because it doesn't yet exist, or there may be security concerns with using the actual data, or it may be just too much of a hassle to get the actual data. Maybe you even work in a developer relations team like ours and want to tell other people about new features and build out cool videos. In any of these cases, it may be helpful to just generate the type of data you're interested in so that you can try out and learn about Druid's features. This is where a data generator comes into play. Let me at first take a moment to explain where this data generator came from. Early in my career, I worked for companies that created hardware storage devices. I usually worked in a performance architecture role where it was my job to determine the performance characteristics of a device based on its design. I did this by creating very detailed discrete event simulations, which allowed me to simulate these storage devices for various workloads, and then measure the various aspects of their performance, including not only response times, but also queuing times and utilizations for the various components. As a result of this work, I gained a lot of experience in simulating workloads. Fast forward some decades, and I found myself working at Imply creating Druid training courses where I needed some example data. And I wanted to allow people taking the course to be able to customize the data to make the data look more like what they are actually working with. So, I applied the experience I acquired early in my career to create a Python program that generates simulated data according to a configuration file. Here are some of the characteristics of this data generator. It's a Python program, so it can run just about anywhere. It can generate data to standard out a file or even a Kafka topic. It can generate records of different types, or in other words, records with different types of timestamp, attributes, and measures. The data generator can simulate events based on a sequence, like you might see in clickstream data. It can generate dimensions containing all the common data types, including string, int, float, and even IP addresses and timestamps. If you're learning about Druid, you may have taken some of the courses that we created, and you'll also want to pick up the data generator. You can become a real expert in Druid by generating data with different characteristics and applying what you've learned. In this presentation, I'm going to cover how the generator works, how to run the generator, and how to configure the generator. Let's dig into how the generator works. The data generator uses two key ideas, emitters and a state machine. Emitters are components that generate events or records according to a description within a configuration file. We can configure multiple emitters such that each one generates a specific record type. For each of these record types, we can specify what dimensions the record contains, as well as the type of data for each of these dimensions, along with their cardinality and distribution of the cardinality. When we talk about cardinality, we mean the number of distinct values that a dimension may contain. The distribution of the cardinality has to do with the relative frequency with which the various values occur. For example, imagine a dimension named dwarf that contains the names of Snow White's close friends. There are 7 different names, so the cardinality of the dwarf's dimension is 7. The distribution of the cardinality determines how often the various values show up in the records. As an example, a uniform distribution would cause each of the 7 names to have the same likelihood of showing up in the dwarf dimension within a record. Alternatively, a normal distribution would cause some of the names like Dopey and Sneezy to occur more frequently than others like Grumpy and Doc. We'll see later in this presentation how we can control all of this with a configuration file. The second key idea of the data generator is a state machine. A state machine is a model that simulates transitions from one situation or state to another. We can use state machines to simulate entities that cause emitters to generate records. For example, if we want to generate clickstream data, we would want to simulate a user navigating a website. As the simulated user moves from page to page on the site, the data generator might cause the emitters to generate records, which would give us data that correlates well with the actual site users. So, by combining the state machine with emitters, we can create representative example data. Given a cursory understanding of how the data generator works, let's briefly look at how we install and run the generator. To run the generator, the first step is to clone the GitHub repository. The actual URL for the repository is github.com/imply-data/druid-data generator. Within the repository, we find a README file that contains all the documentation that explains how to configure and run the generator, the Python program named druid-data-driver.py, and an examples directory which contains several example configuration files. If we look at the README file, we see that the top section of the README file details which Python libraries we need to install and how to run the program. Notice that there are several options available to us when we run the program. The -f option allows us to specify the configuration file we want to use. If we don't specify this configuration option, the program will try to read the configuration from standard in. We can run the program in one of two modes. The default mode, which is a real-time mode, allows the program to use real-time delays between events, so the mode simulates an actual workload. Alternatively, we can use simulated time by specifying the -s option. The -s option lets the program generate events using simulated time, so there's minimal wall clock delay between events, which can be helpful if you want to generate a large batch of data as quickly as possible. The other two command line options are the -n option and the -t option. These options control how long the program runs, and they are exclusive, meaning you only use one or the other. We use the -n option to generate a specific number of records, and we use the -t option to allow the program to run for a designated period of time. If we don't specify either -n or -t, the program will run without stopping. Now that we see how to run the program, let's dig into the configuration file. There are 4 sections in the configuration file: the target specification, the emitters list, the inner arrival specification, and the states list. The target specification allows us to determine where the resulting JSON records go. Currently, there are 3 possible target types, which include standard out, a file, or a Kafka topic. When we specify a file target, we can specify the output file name. For a Kafka topic, we specify the IP address and the topic name. That's all there is to the target section. The next section in the configuration file is the emitters list. The emitters list is a list of objects, called emitters, that the generator uses to generate records. Each emitter consists of an emitter name and a list of dimension specifiers that generate values for each record instance. However, before we dive into that, we need to lay some foundation by understanding the various distribution specifications. Various objects within the configuration file use stochastic, which basically means random, values. A distribution specification is like a function that tells the generator program how to sample stochastic values, and we can use these distribution specifications whenever we need to use stochastic values. The generator supports 4 different distributions, which include constant, uniform, exponential, and normal. The constant distribution restricts generated values to a single value. When we use a constant distribution specification, we designate the value we want the distribution to always return. So, if we always want the same value, we use a constant distribution. The uniform distribution selects values from a range, where each value has the same likelihood of being selected. So when we use a uniform distribution, we need to specify the minimum and maximum values in the range. The third type of distribution is an exponential distribution, which selects values based on the exponential function. This means that some values are selected the majority of the time and other values are seldomly selected. In the case of the exponential distribution, we specify the mean of the generated values. Finally, the last distribution is a normal distribution or a bell curve distribution that selects values based on a normal distribution function. Therefore, to use this distribution, we need to specify the mean and the standard deviation of the function. One thing to note about both exponential and normal distributions is that sometimes we need to force the results of these distributions into bounded values, for example, when we need to generate a stochastic array index. When this occurs, the generator will truncate the distribution values so that the values are within the bounded range. This can result in unexpected behavior, so be careful when using these distributions in a bounded fashion. Armed with this understanding of distributions, let's look at the various dimension specifiers for emitters. As a reminder, emitters are the objects that generate record values, and dimension specifiers are the objects within the emitters that generate the values for the specified dimensions within the record. So, the first thing we designate when creating a dimension specifier is the dimension's name and its data type. Currently, the generator supports 7 different dimension specifier data types, including enum, string, int, float, timestamp, IP address, and variables. Most of these types are self-explanatory except for maybe enum and variables, so let me explain these two special emitters. Enum data types are merely a finite list of designated values, and enum dimension specifiers stochastically select one value from the list. Variable type dimension specifiers select values based on key value pairs that the generator created at an earlier stage of execution. We'll explain more about variables when we discuss the state machine. For enum dimension specifiers, we specify the list of possible values and the cardinality distribution. The cardinality distribution designates how the dimension specifier samples from the list of values. Most commonly, we will use a uniform cardinality distribution with enum dimension specifiers. The one exception to this would be if we want a dimension to have a constant value, in which case we would create a list of a single value and use a constant cardinality distribution that returns a value of 0. Finally, in the enum dimension specifier, we can designate a percentage of nulls that the dimension specifier will generate. This percentage of nulls is an optional setting, and when omitted, no null values get generated. The percentage of null values actually applies to all other dimension specifier types except for variables. The string dimension specifier generates character strings of potentially variable lengths. In the string dimension specifier, we can designate a list of possible characters the dimension specifier will use to create the strings. If we omit the list of characters, the dimension specifier will use any printable character. We can specify the length of the generated strings by using one of the 4 distributions. One final thing we can optionally specify in the string dimension specifier is a cardinality and an associated cardinality distribution. The way cardinality works is that the dimension specifier creates a finite list of values, and then the cardinality distribution determines how the dimension specifier samples from those values. We can use this cardinality concept for most of the other dimension specifiers except enums and variables. The int, float, timestamp, and IP address dimension specifier types all select values based on a distribution and include the cardinality and the percentage nulls that we previously discussed. That sums up the explanation of emitters, so let's turn our attention to the state machine to see how and when emitters generate data. As we mentioned earlier, the state machine allows us to model an entity as it performs a process that causes record creation. We can think of a state machine as a directed graph where all entities enter the graph at the first node and then probabilistically transition from node to node. Eventually, all entities transition to a stop node where they exit the graph. In this graph, the nodes correspond to states within the modeled system. As an example, consider a person browsing an e-commerce website. We can model this with one state for each of the various pages on the site. The transitions between the states correspond to links between the pages, and we associate a probability that an entity, which is to say a person, would select that link. In the data generator, when an entity enters a state, it performs 4 actions. First, the entity creates or updates any desired variable values. Second, the entity emits a record. Third, the entity delays for some stochastic period of time based on a distribution. And finally, fourth, the entity selects a transition to a new state. I promised I would discuss variables. Perhaps now is a good time for that. As I mentioned earlier, variables are key value pairs that allow us to maintain some context between states. In our website state machine example, we might want to have a session ID as part of the records we emit. We can set the value of this session ID when an entity enters the initial state, and then include that value as a variable dimension specifier in the various records that the state machine produces. We describe the state machine in the configuration file using a list of state objects, where the first state object in the list is the initial state. Each state object has a name, an emitter object, a list of variables, and a delay specification and a list of transitions. Each variable in the list of variables is just a dimension specifier, where the name of the specifier becomes the name of the variable. The delay specification is a distribution specification as described earlier. Finally, each transition in the list consists of the name of the target state and the probability of taking the transition. Of course, the sum of all transition probabilities for any state must equal 1. The fourth section of the data generator's configuration file is the inner arrival specification, which is merely a distribution descriptor that designates the amount of time between entities entering the state machine. Let's wrap up this presentation by showing you the data generator in action. I will run the program using the clickstream config.json file from within the examples directory. We can see in the config file that this example has 4 emitters. We use the first emitter, named enter, to set the values of some variables when an entity first enters the state machine. The other 3 emitters generate records at various points in the state machine and are named hit, purchase, and leave. The state machine models a user browsing an e-commerce website and consists of 7 states. The home state is the initial state, which represents users first landing on the website. This state fires the enter emitter, which initializes several variables representing the user's context. The leave state is the final state, which represents users leaving the website and emits the leave record. The job state represents those users that come to the website looking for employment opportunities. This state emits a hit record indicating a page hit. The products state represents a product's catalog page and also emits a hit record. The last 3 states, named big widget, medium widget, and small widget, represent specific product purchases, so these states emit purchase records. We can inspect each of these states to see their respective delays, which is the amount of time we have modeled for the user to spend in each state, and the probabilistic transitions from the state. One final note about the config file. We see the inner arrival distribution, which describes the delay between entities entering the state machine. In this case, the entities enter on average every 1/10 of a second based on exponential distribution. From a queuing theory perspective, the exponential distribution is a good way to model an unbounded number of independent entities arriving. We can run this configuration using this command, where we will run for a total of 10 seconds and pipe the resulting records into JQ to make them easier to read. So there you have it. We have reviewed all you need to know to be able to start generating customized data so we can effectively prototype our Apache Druid clusters. We hope this data generator will be a helpful tool for those in the Druid community.